Hi, welcome to Physics Teacher. So I got a comment in a previous video asking me for how to calculate, or what are the formulas to calculate the mass of an electron and of a proton. Now to do that, I've made this video where we're going to compare a cathode ray tube with a mass spectrometer. Alright, so before we compare these two devices, we first need to talk about the force that a charged particle undergoes when it's going through a magnetic field. So that's called the magnetic force, and it's going to be equal to the charge on that particle times the cross product between its velocity and the magnetic field strength B. Now this cross product we can just write as a geometric cross product, which would be the magnitudes of velocity and magnetic field times the sine of the angle between velocity and magnetic field. Now in both the CRT and the mass spectrometer, we send charged particles through a magnetic field at 90 degrees. So it's always perpendicular because that gives you the greatest possible force for the magnetic force. And so the sine of 90 would just be 1. And so we're left with that magnetic force equaling QVB. All right, so let's now look at the CRT. So J.J. Thomson created and used the CRT, the cathode ray tube, and he used it to first discover the electron. So how that worked is, well, he heated a filament, which then shot electrons. He didn't know what they were at the time, but then he accelerated them through parallel plates. So he gave them a certain velocity, so they're moving pretty fast now, and then you can send them through another set of parallel plates oriented at 90 degrees to the first set. And if these are all negative charges, what we can do is make the top plate to have a positive charge and the bottom plate to have a negative charge, and those particles, which are electrons, will feel an upwards electric force and be deflected to a point let's call X. And that will be due to this upwards electric force. Now he also has coils. In these coils you can put current through them, and they will cause a magnetic field going, in our example here, into the screen. So we have a magnetic field going into the screen that we call B. And what happens then is that causes a force, a downwards magnetic force. Now, if you're interested on how I know it's downwards, let me know in the comments and I'll create a video going over all the right-hand rules for electromagnetism. But for now, based on the cross product, you know that the direction of that magnetic force will be perpendicular to both the velocity and the magnetic field. And so let's say it gets deflected down towards Z. Now if you turn them both on and adjust them so that the electric force is equal but opposite to the magnetic force, then its path will not deflect and it'll go over here towards Y. Alright, so let's start with step 1. What did he do first? First thing he did was leave this electric field off. So we only had a downwards magnetic force. And then when that happens, the particle is going to curve or bend downwards, right? With some sort of radius to its path. So, or some radius of curvature until it exits that magnetic field, and then it will continue straight towards Z. So the magnetic force, since the magnetic force is always perpendicular to the velocity, then it is also a centripetal force. So we can write the magnetic force as shown before as QVB, and the centripetal force will be mv squared over r, where r is your radius of curvature for that circular path that it undertakes while inside the magnetic field. Now, what J.J. Thomson did was he rearranged this to solve for a charge to mass ratio, which currently we would have as V over BR. So then what J.J. Thomson did was turned on the electric field and adjusted it so that the electric field will be equal to, or the magnitude of the electric field will be equal to the magnitude of the magnetic field, which then will cause our beam to continue going straight due to its equilibrium. Alright, so this here, the electric force, we calculate that as the charge times epsilon, where epsilon is the electric field strength. And that's going to equal the magnetic force, which is QVB. And if you rearrange this equation for V, since charges cancel, we simply get epsilon over B. Now we can sub this back into equation 1 for velocity, and we get the charge to mass ratio to be the electric field strength divided by the magnetic field strength squared times by that radius of curvature that it undergoes under that magnetic field strength. Now, if you're not sure how I calculate epsilon or the magnetic field strength, just let me know and I can make another video going over parallel plates and Ampere's law. Now, when J.J. Thomson calculated this, he calculated that charge to mass ratio to be 1.76 times 10 to the 11 coulombs per kilogram. And then he combined this with an experiment done not too long before by Robert Millikan called the Millikan experiment. And again, if you want to know about the Millikan experiment, let me know in the comments. But he got the charge, or the elementary charge, which we sometimes just call E, for the elementary charge, which is the charge on an electron, which is also the charge on a proton, to be 1.602 times 10 to the minus 19 coulombs. And when you combine that elementary charge in this equation, J.J. Thomson calculated the mass of these particles to be 9.11 times 10 to the minus 31 kilograms. At the time, smaller than any known particle, which was the hydrogen atom at the time. So J.J. Thomson, with that, discovered the electron and its mass. Alright, so next let's go to the mass spectrometer. Now, J.J. Thomson's cathode ray tube is what led to the invention of a mass spectrometer. And you'll see that it is similar in a lot of ways. So we do start off with parallel plates, which are used to accelerate any charged particle. So you wanted to know the mass of a proton. So let's take protons then and accelerate them so that they're moving at some high velocity. And then we just send them into a magnetic field. That's it. We don't have an electric field and a magnetic field like the cathode ray tube has. We only have a magnetic field, which would cause the path of whatever our charged particle is to bend. Now, in this case, if we have a positive proton going through this magnetic field, which is into our screen, path is going to curve upwards, like so, at some sort of radius of curvature r. So we know, due to that magnetic force as it passes through, our magnetic field is going to be equal to the centripetal force, just like we did before. With the cathode ray tube, we get QVB is equal to mv squared over r. Now, what we also do is we want to know the speed as it goes into it. So how fast do these parallel plates accelerate that particle? Well, to calculate acceleration, we're going to look at conservation of energy, or the work done by the parallel plates. And that is the charge of the particle in the parallel plates multiplied by the potential difference between the parallel plates is equal to kinetic energy, or change in kinetic energy, which is 1/2 mv squared. Mass times velocity squared. Alright, so here we have two equations then. We don't know what velocity is, so let's sort of solve for velocity in our first one. So I'll get velocity as 1 will cancel, so we get QBR over m. And if I substitute that into our second equation, this gives us, well, we have Q times delta V is equal to 1/2 mass times all of this QBR over m squared. All right, so let's apply that square to everything in our bracket. So we have Q delta V is equal to, we can bring this half over here. So 2 times Q delta V is M times by Q squared, B squared, R squared, all over M squared. So let's cancel some things out. So here we have a Q here and a Q squared here. Here we have an M and an M squared. And there we go. Now when I rearrange to solve for M, I'll get M equals, so I'm cross multiplying essentially, bringing the M up here and the 2 delta V down there. We get Q, B squared, R squared, all divided by 2 delta V. And that's the equation for a mass spectrometer, slightly different from the one we used in the cathode ray tube. And it can be used to find the mass of any charged particle. And for a proton, we get the mass as 1.67 times 10 to the minus 27 kilograms. I hope this video helped, and if you have any further questions, let me know in the comments.